Okay, thank you, Marcus. Thank you for the nice introduction, and thanks for inviting me for this talk here. Much of things which I intended to say have already been said by Vedat, so my talk might be a little bit shorter. And as a mathematician, I would just start here with a motivation where we do some simulation and that we are working hand in hand with laboratory, and this is not competition. Either you do it in the laboratory or you do it in the simulation in silico versus in vitro. No, it's just working hand in hand, and this can be shown by the following example. So you see here, on the one hand you might see there is the laboratory, and on the other hand you can say, okay, there are the simulation methods where we have computer experiments, and we call these methods in silico methods, and the other ones are in vivo or in vitro methods. And one example is altenariol. It's a mycotoxin. And you find it, so for instance, in wheat, and in the late 80s, where they found in a region in China in the wheat this mycotoxin, they saw that the people get esophageal cancer, and so they thought, okay, this might be due to the fact that we have this altenariol in there. And so they wanted to know the true structure, because one theory was that it comes to an intercalation. What is an intercalation? Well, imagine yourself, we have the DNA. This is something like a curl, and that it blocks, that this has a planar structure, and this planar structure is getting into this DNA so that the DNA can't move as it is used to. So for them, it was really important to know the structure of the altenariol, and if they know the structure of it, they can say something about the behavior in the body, and this was the starting point for laboratory experiments. And so from the chemical point of view, we learned that it might be planar because we have these benzoyl rings, and it has kind of an aromatic structure. I'm not a chemist, so this is what they said to us. And then we did a simulation, and we ran this over a certain period of time, and then we saw that it has mainly these two conformations, so these two states. And as Marcus already said, as Mr. Stein already said, this is a statistical way. This is not that the molecule only has this state and this state. It's just that it has mostly this state or mostly this state. These are representative of a statistical, let's call it cloud, where they are looking pretty similar to this. And so we identified these two conformations, and then we could say, well, mostly, in most cases, the AOH, so altenariol, is non-planar, and so the theory which they had concerning that it might happen there with the problem with this intercalation with the DNA, this will not be. And later on, when we finished this project, they did, for some reason, for another reason, also this in crystallography, and they detected that this is non-planar, so they really said that it is true what we discovered. And this is a really typical example from working hand in hand with the laboratory, working together on one level, and that we can help each other, that there are so many synergies which we can use. But now, let us head back. Why am I as a mathematician here? Where are the problems in there in this simulation? And well, we consider mainly such a simulation problem as a multi-scale problem. What is a multi-scale problem? It means we have different scales of models where we can do some simulations. So on the one hand, we have this quantum molecular model, which is really, really accurate and gives us a detailed information about the molecule. In between, we have an atomistic model. This is basically what Vedat said there. This is the classical molecular dynamics. This is something where you have a force field, and then there are some coarse graining methods where we just collect some variables and try to explain it on a coarser level. And so this is the trade-off. On the one hand, I really want to do this and with a high precision, but due to the computational burden which I have on the quantum mechanics, I'm not able to resolve the whole molecule. So I need a switch and a trade-off between all these methods. One method might be to do an adaptive approach, meaning I know from a whole molecule one part where I need a really detailed resolution of it and a real detailed simulation. So maybe you would simulate the whole molecule in classical molecular dynamics, and in one part of it where you need this detailed information, you go down to this quantum mechanical level. And as Vedat already said, so we are interested in the movement of the molecule, and in particular in protein folding, we are interested in how the molecule moves onto its final structure. And he already said that this is a very time-consuming method, and that we have to wait or simulate pretty long to see such an event as the protein folding. So one question might be, why not just using, if we have something like a time integration, why not just using a coarser time step? So why do we have a resolution down to femtoseconds? And the answer is simply given by that we have within one single molecule various different time scales. So if you have these local motions, which you find in some side chains, we are here around the femtosecond regime, and in the mesoscale, so this is the name we call it, it's subunit motions, and this folding is on a really large scale happens. And we have to cope with all these details and still to capture the really fine scale resolution, because the information here in femtoseconds is not allowed to get lost. So these are the challenges which we have. And another challenge, so these were the scale challenges which I said. And beside this, from the mathematical point of view, in this phase space, each point represents a conformation, so a state of the molecule. And for larger molecules, this state space can get really, really large and high dimensional. And this high dimensional is, of course, a computational burden. So these are the challenges in the time scale and in the length scales, and of course in the dimension, curse of dimensionality, because we know when we are working in high dimension, then many methods which we use in lower dimension are not possible to use anymore. And another thing is that most models, mathematical models, minimization models, are pretty good in finding the closest local minimum. So local minimization problems, there are many methods which you can use, but the problem is, if we have a look at this at the energy landscape of a molecule tends actually to get the states of the lowest energy. But the problem is, it has not this at the beginning, it just tends to this lowest energy value here, down here. And before, there are these local minima, and these minima cause that the problem are there, and if you use a normal minimization problem, you get stuck in this, and this is the thing that Vedat already told. And these states which we have here are distributed according to the Boltzmann distribution, and as I already told, the challenge is that we have this high dimensional problem. Okay, so the challenges, well, these are computational challenges, but there are other kinds I will not want to talk about, so that is not working here. Okay, so we have everything together, and right now we could start with the simulation. So we could run this, and here this is nothing. Yeah, there it starts. And here you see we are running such a molecule over a long certain time. This is beta amyloid. It's and plays a role in the context of Alzheimer, and we run this simulation according to the Newton equations of motions with a certain force field, and we compute it and compute it and compute it, and we see a lot of moving pictures, but actually we learn nothing. So the question is, what can be done with simply these things? These are so many data which we are generating here, but we can work really with this. We can do something with an eyeball norm and can say, well, now it's more stretch or not, but how can we work with these many data which we are generating there? And Control L. And the answer is to take advantage of the local subunits which we had at the beginning. You remember this folding funnel which I showed you at the beginning, where this molecule wants actually to go here into this very low energy regime. We have these subunits here, and we try to take advantage of this because we know, comparing to this, as Vedat said, so the molecules stay very long time in these states and only rarely switches between them. And so here what we did is we simulated Bhutan over a certain period of time, so long time step, and then we observed this. This is actually exactly the same, but you did it with Pentan, didn't you? I don't know. No. Okay, so maybe it's the same. And you see that this molecule is staying mostly in this part and this part and this part, but only rare transition are in this. And we call this state that the molecule is mostly in one state, but it's not really stable in this state. It's metastable, meaning that it stays for a very long time. So from the mathematical point of view, if we know that the system stays for a pretty long time in this metastable states, so the task would be identify these metastable tasks, and if you have these metastable tasks, then compute the transition probabilities between these metastable states, and then you can explain the whole molecule on a coarser scale. Coarser scale is good because it's less computational burden. And additionally, we know how to solve these huge amount of data and how we can an idea of treating these. And so from the mathematical point of view, this will be the very first level. We have some reversible dynamics. This is what Vedat also showed at the beginning. He used some Stromer-Verlet integration steps. So this will be where we have all the states. And instead of having a look at only the points, we are collecting these points, and we have a look at the evolvement of the densities. So we are moving the densities where there are conformations or states collected together and how they evolve. And this would be the Fokker-Planck operator or Fokker-Planck equation. Then we compute a transfer operator and generator, and from this generator they will compute this transfer operator. There's much of theory behind this. I will not go into details, but right now I will stretch out why do we want this transfer operator. What is so good about this, and why are we heading from this way here via mathematical complicated schemes into this here? This can be best explained by this little example here. So this is molecular dynamic simulations, and we have this potential here, and as you can see, we have mainly these three minima here, these local three minima. And if we did this cascade, which is showed here, down to this transfer operator, and if we have compute this transfer operator, then the eigenvalues of this transfer operator give us an idea where to find this metastable states. The transfer operator says us what is the average probability that the system starts in the states and maybe stays in another state. Or we can also use this starts in the states and still stays in the states. Starting in the states and still staying in the states is pretty similar with eigenvalues of this operator being close to 1. And so you can see here the first three eigenvalues of this particular problem, which has been taken by a publication of Schütte. So this theory was mainly developed at the Zuse Institute. And you can see here that developing this transfer operator and getting the first eigenvalues, we see that the first three eigenvalues are close to 1. The first one has to be 1. This is due to the fact of the Perron-Frobenius theory. And the other ones are really close to 1. And then we have something like a gap. So we are using these first three eigenvalues and its corresponding eigenfunctions here. And we see that they have on these this is here down on this the same scale as up here. So we see that these eigenfunctions corresponding to the eigenvalues, that they really have a special structure within this minima. So they are almost constant here. And additionally, if we change between these two states, we see that we have a sign change or a dramatic change also here in this eigenfunctions here. So taking this transfer operator, which has to be generated, we can solve the eigenvalues, and these eigenvalues, the corresponding eigenfunctions, give us an idea of how to identify these minima. Once again, we wanted to find these minima and local minima to describe the whole system in terms of transition probabilities, because the whole system will mostly stay in these states. Okay, so this was a small example, but now the question is, how can we do this with a larger example? And this is cyclohexane, and so we are doing a simulation, and we are collecting once again this data, and we get something like a probability cloud. So you can find here these clouds, and this cloud represents the number of states being in, well, this state almost, so comparable to this. And we know that these distributions here, that these states which we are having here in this cloud, that they are mainly distributed according to the Boltzmann distribution. And actually one could say, well, it's pretty easy, just compute it. But this potential which we have here, this is a global potential, and it lives in a really high dimensional space. So as I already said in this one-dimensional example, just keep this in mind with this one-dimensional example. So our goal is we want to compute transition probabilities to describe the whole system. What is the probability of starting in this state, or in one representative of this state, and ending in this state? This is what we are interested in. We can see this as a Markov process with a transition matrix. We can interpret this in this way, and to do so, to come to this very comfortable coarse-grained description, we need once again the transfer operator, and this transfer operator allows us to compute these transition probabilities. Having now those transition probabilities, we are still in an infinite dimensional space. So this is functional analysis from the theory, but actually we want to work in a finite dimensional state. So also very important, from this transition operator, we know we need the eigenfunctions, and having the eigenfunctions allows us to identify these states here, and then we can give these transition probabilities between these states. And but the problem is, how do we get these eigenfunctions and eigenvalues? Eigenvalues is not that bad, but eigenfunctions, they have to be computed somehow. And the idea is, since we are in an infinite regime, we are using a Galerkin discretization, and we need something like a basis, some basis function, and these basis functions, they have to meet the partition of unity condition. So this is, we want to project this operator, where we want the eigenfunctions of these operators, we want to project it on a finite dimensional space such that we can give an n times n transition probability matrix, giving us the probability to start in a certain state and moving into another state. So this will give us a finite regime, and the question is, how do we get this finite dimensional regime? And to do so, we are using mesh-free basis functions. Why mesh-free basis functions? Well, the reason is mainly we are in a high-dimensional problems, and other method would fail due to the curse of dimensionality. And these kind of basis functions, or Voronoi discretization, does not have this curse of dimensionality, or not that bad. And so we can do some points here in our cloud and then identify it with these basis functions. And so we have these portions of the transition of this density. So the main idea here is, instead of treating the whole problem at all, we are just having a look at small portions of the system. Having now a basis, we can then do a Galerkin discretization and then finally obtain a generalized eigenvalue problem. And this generalized eigenvalue problem, if we have solved this, then we can give the transition probabilities of this operator in a finite dimensional space. So this is the core scale which we are interested in. And the problem is, so far so good, we are actually getting down here on this finite dimensional part. We know that this transfer operator gives us much information, that these eigenfunctions are very interesting, but we need to resolve this. And now we have found this and define it on a lower dimensional space, but the problem is we have to solve these two scalar products. And this is not an easy task at all, because these scalar products live in a high dimensional space. And the trick is to consider these scalar products, which have to be computed here for the eigenfunctions, in a certain way. Have a look at first, what are these basis functions? These basis functions can be shown that the structure of the basis function forms a partition of unity, and we have these mu. This is the global distribution, and this is the problem since it's global. And the idea is to combine them so that we only need to compute here these localized potentials. So meaning we want to resolve the whole system, the global potential, but instead of doing this, we are just dividing the whole space which we have. We are simply dividing it into small portions, and these portions are defined by the basis functions, and we compute only for each basis functions the density. This can also be localized by this localized potential. So instead of running this really long-term trajectory over the whole space, we are just having these confined trajectories. And then these confined potential can also be interpreted as a global potential, and where there is a harmonic constraint, and this constraint is given by this basis function here. This is basically what I wanted to say, this localized basis function, and summing all this up, having all these portions and computed all these local densities, we can sum this all up, and then we obtain the value for this scalar product, which finally allows us then to compute the eigenfunctions of this operator in a discrete setting. The question is, actually, at the beginning, I told you that I want to identify sets in this phase space where they are similar, and then I want to give some transition probabilities. But I have not yet told how to identify these sets, because we simply did this discretization by mesh-free methods, but there is no idea how to combine these metastable sets, so states which are similar, and this can be done in the following way by a tool which has been developed by Markov in 2005. It's called PCCA, and GemPCCA is a product which we developed in the last year. It's also capable to use for a broader class of molecular simulations. And the idea is we want to identify this portion of the system where the metastability is in there, and these portions are simply the linear combinations of these eigenfunctions. Of course, when we have these mesh-free basis functions, we don't have really these hard boundaries, so we are losing that we have something like a transition probability, but this can also be interpreted in the terms of membership functions. And this is heading to the direction with once again, Mr. Stein said that we can say that we don't have really a bounding, but we have something which has membership being close to bound. And so we can identify these states. How to solve these coefficients, because these coefficients determine the metastable states, as a challenging task which has been solved in PCCA+. And so if we have used this PCCA+, then we are able to simulate the whole molecule with all the states and all the long-term trajectory ways we saw at the beginning, this huge amount of data. We are allowed to have a Corsa scale, and this Corsa scale gives us the information of the molecule in terms of transition probabilities as we wanted it. That's all. Thank you.
Yeah.